So who are we? Well, we're not in sales, despite the way that we look. But,
despite the way Ben is dressed, we're not in sales.
Yeah. Basically, just some of the things we've worked on over the years. Too far. So this is a huge subject, and it really is just an attempt to give you a high-level overview of how you would go about doing concurrency. So should we start with a quick show of hands? Hands up if you're using Java 4 as your main VM. Nobody. Wow. Hey. I like giving talks in London. Yeah. If you do that in Atlanta, half the room puts their hands up. Yeah, how about depressing. 5? Anybody stuck on 5? Yep, two few people. Oh, good. I suppose everybody else is on 6. Anybody on 7? Yeah, well.
There's always one. Well done, Russell. Good man. Anyone on OpenJDK 8 already? No?
Well, I've got it on my Mac.
That's Mr. Barker.
Yes. Okay. So really, this is not a new subject. I mean, this has been around for a long time. Going back to Java 5, you have things like Java util concurrent start to come in, and this is really a big subject which has had some refinements in 6 and has got some new stuff coming in 7. But a lot of people don't really do it. I mean, there are still loads of people out there who despite the fact they've got a Java 5 or a Java 6 VM, they're still writing code which is mostly thread, timer task, all of those kind of classes, rather than the
new nice new ones like lock and condition and.
So we started to have a think about this and thought, why is that? Why do people still use old Java 4 style concurrency, especially in prod code?
And we're going to expose some people's dirty little secrets here. Who still uses a synchronized keyword in their concurrency code? Come on, don't be shy. You can admit it. It's okay. A couple of people in the back. Yeah.
So why aren't people using it? That was my question. Some people think they've got too much legacy code. They think that it's going to be an absolute nightmare to refactor it all. Some people don't know that it's actually easier to write Java util concurrent. For some reason, it seems to have this cachet and this feeling that people are scared by it, and they think it's going to be much harder to use than thread and synchronized, or maybe they've just had such bad experiences with writing synchronized and having these incredibly complicated locking strategies that they've had to write, that they think all concurrency code is always horrible and evil. The other point was that when we started talking to a lot of people that were coming out of university, we found that lots of people really weren't still being taught it at universities. If they did any threading at all, it was still synchronized and it was still thread and runnable. So the word is still not really getting out there as much as it should do, which is a real shame, because you have some real experts. You have people like Doug and Brian producing incredibly interesting work. I mean, their books are both absolute classics in the field. And there's there is a lot of really interesting research which is happening as well.
So interestingly, only very recently is Oracle actually updating its official training material for its certification, and only now have they actually started to put Java util concurrent into this for Java 7 onwards. And it's been around since Java 5. So even Sun/Oracle itself seem to refuse to eat its own dog food, which is quite odd.
Okay, so another reason. Maybe there weren't enough otters in it. So, seriously, otters. So, all right.
We told you it was going to be a light and fluffy talk.
Yep. Why otters? Well, otters are actually a really good metaphor for concurrency, because they're long and thin and they look a bit like threads. But they also, they're also very curious and mischievous, and they tend to run off in random directions, and they're capable of wreaking absolute havoc if they're not contained and properly controlled. They can be very, very sneaky, and if you've written a lot of concurrent code, you know that having this idea of having a bunch of things with a mind of their own at times, it seems, is actually quite compelling.
Does anyone here have small children? Yeah, and you've been to one of these like little school days or creche days where they all get let loose out in the park? Same idea. That's what threads are really like.
And there is actually a very serious point here. The point is that when most of us were learning to program, we all, judging by the sort of average age in the audience, we all learned to program on machines which were single core. And that means that our worldview is based around serial code. And it's actually quite a big step to actually start thinking about what happens when you have multiple cores and have multiple areas where code can be running at once. And learning to think in ways which are inherently multi-core is, as we'll discuss, it has to be the future, and it does represent a bit of a mind change. And if the QTotters help you to realise that that you need to have a new mental model for thinking about programming in a concurrent way, then so much the better. So let's do some auto management, which in practice is actually often called concurrent type safety. That's kind of the big buzzword here. And what that means is, if I've got a whole bunch of objects which are running in multi-threaded code, do they stay self-consistent, no matter what else is happening? And basically, these four forces, which are actually due to Doug Lee originally, they come in two pairs. And the two pairs are the safety and liveness pair and the performance and reusability pair. And here's some bad news. These four forces actually act against each other. So you want to have code which is both safe and live, but at the same time, those two things are in some senses in opposition to each other. There are concerns that the more safe you make the code, the more locking is involved. Java as a platform is inherently wedded to the idea of mutable state. I mean, Java the language and also Java the bytecode. And the only way that you can protect mutable state and keep it safe is by applying locks. So those ideas of mutable state and locks, you're probably going to get really sick of hearing about those because they are absolutely key to understanding why concurrent code is hard and also to writing safe code.
We know some people here absolutely hate them, and they will talk about that later on tonight.
Yep. And so liveness basically says, does my multi-threaded code actually ever progress? Does the operations progress? Do methods actually ever return? In extreme cases, you can have things like deadlock, where two threads are holding locks in such a way that they can never release them. That's a pretty permanent failure of liveness. But there are other liveness problems that you can encounter as well. And building systems where you can prove, or you can be reasonably sure that the system will not just grind to a halt is really pretty essential. And then performance and reliability. These two are kind of the lesser pair of forces. Safety and liveness are the big two. These guys are kind of the second string pair. And writing reusable code is very difficult. I mean, and that's why a lot of the focus is on having toolkits like Java Util Concurrent and some of those frameworks, is because they really are the best toolbox that we found for producing code. And trying to write your own reusable thread pools is very, very difficult to get right.
But there's an interesting thing about performance. When multi-core processors first came out and the hardware manufacturers were touting the wonderful new things that this stuff was going to do for you, no one had actually written any software for it yet.
Yeah.
So for early adopters of multi-core hardware systems, there was actually very, very little even operating system software that could actually support it properly. And it's still true today that a lot of programming languages and things are catching up. So
yeah. So until very recently, people basically only had one processing core. And what that means is that when you're doing multi-threaded code on a machine with a single core, it's not really multi-threading, because there's only one core, so there's only ever one thread running at once. And what's actually happening is it's really time sharing. You're really sharing the CPU between different threads. And that means that you're interleaved on a single core. And that actually can mask errors, which so you can actually be more forgiving because you're really only time sharing than you will on a system which actually has multi-core. And it does mean that you also tend to think in a very serial way. But as we know, as we saw in Simon's talk, we have had a change recently which has meant that we have to start thinking multi-core. And at the heart of this is Moore's law, which basically says you can get more and more transistors on a chip, but the corollary that we've seen in recent years is, despite the fact that we've actually got a lot more transistors, and that trend is still going strong, the clock speed has flattened out, and other characteristics of chips which are related more directly to clock speed, because transistor count's not really a particularly good way of relating to clock speed. So transistor count is just how much space you've got on the chip to build functionality with. And what's actually been happening is because Moore's law really is only about transistors, things happen which is what you can think of as the memory latency exponent gap. If I flick back to this slide, you can see this is a log linear graph. So this line is straight, and it takes about 6 or 7 years to cross one of these vertical divides. So a tenfold increase in 6 or 7 years is about doubling every 18 months. So that means that this graph, if it was a linear scale, would look exponential. Memory is also getting faster exponentially. But the problem is the exponent is a lot smaller. So there is a widening gap between how many transistors you've got and how much silicon you've got available to develop processing features and how fast your memory is. That's a problem. Because even if you can keep the clock speed going up, you find yourself not being able to keep the pipeline full. So the CPU is able to work, but it has nothing to do because it's waiting for the data that it needs for the next step of the calculation to catch up. What that means is that effectively you need to spend your transistor budget on doing tricks. You have to go to more and more complex contortions, just like this guy here. And you hear people talk about ILP, instruction level parallelism, and CMT, chip multithreading, and branch prediction, and all those kind of things. And all they're really doing is they're finding ways to spend the transistor budget in such a way that you can try to keep the pipeline full. They're more and more complicated tricks, but ultimately you're chasing diminishing returns. There's only so much that you can do with the chip, and ultimately that gap between processor speed and memory latency, ultimately that's going to kill you. There's just nothing you can do about it.
I'm just going to go back one slide and point out a couple of quick things. Who here actually comes from a C or a C++ background? Yeah. So, do you remember doing things like crafting the size of your data structures just the right size that would fit on the hard drive perfectly, or into the bits of RAM perfectly? You know.
I was more worried about pages.
Right. So, Mike and Trish will talk about this later on Smart with the LMAX talk, but there's this thing called mechanical sympathy. And as Java developers, if you're writing multi-threaded code, highly concurrent code, you're going to have to start thinking about the underlying hardware again. You can no longer afford to forget about how the CPU works and how caches and things like that work. Okay? Yeah. So one of the things you're going to have to do is get back into reading about that sort of level of hardware material.
And that's nothing new. I mean, if we go back into the dim and distant past, there was a time when memory loads to main memory were cheap, and what was really expensive was multiply. So you had to write your code in such a way that it avoided multiply operations, and people would actually do repeated addition rather than take the huge hit for multiply. But yeah, so this sort of period of time, which was it's kind of like a weird Burgess Shale moment in history, where as software people we didn't have to actually care about our hardware platforms, and that's gone. I mean, we're now back in a world where we do have to start understanding the platform again. And if we can't spend our transistor budget on cleverer and cleverer tricks to keep the performance up, well, we'll have to go multi-core. That's all there is to it. There's just no other game in town. And what this means is you end up with separate threads which are executing on separate cores at the same moment in time. But notice that the thread scheduling of the JVM and how that handles Java threads, it doesn't look like OS scheduling. Hands up if you're an Ubuntu user or another desktop Linux. Yeah? Oh, good. Good
awesome.
Numbers.
Yay!
If you open the process monitor with a standard bit of Java code, I mean, Eclipse will do, and just follow the threads and see what happens to them as a Java process is running, what you'll notice is they swap between cores, and they're swapped in and out of the cores really, very quickly. Now, if you write a C program, you'll find that even without pinning, it will just sit on one CPU. It will eventually get migrated off by the OS scheduler, but in general, it won't. So the way that Java threads are running, you shouldn't assume that it's going to behave like the OS. It really doesn't. Okay, shall we do some classic concurrency?
Yeah, we'll do some classic concurrency.
Okay.
Let's have some classic concurrency.
So here we go. And as we talked about, it's about exclusion. It's about mutable states and locks, because this is the Java platform. And here we have a poor excluded little thread, or rotor, which is trapped behind a memory fence, which is preventing it from making progress.
And he's not allowed to go play with the other code.
Yes.
It's all very, very sad.
Yep. So there's a question at the bottom here. Why synchronized? Why is the Java keyword? Because everyone knows what synchronized does, right? It sets up a critical section. It sets up a block of code which only one thread is allowed in at once. Oh, okay. Well, why is it
Seems
called
reasonable.
synchronized? Why isn't it called critical or locked? Right? Either of those would have been fine choices for keywords. Synchronized.
What does it mean? Does anyone know why synchronized is called synchronized?
Yeah. Well, don't tell the others. We'll cover this in the
Keep that one to
slide or
yourself.
two, just in general. Okay. All right. So let's talk about how we could use in the old world 3 approaches to concurrent type safety. And this is really a statement of the sorry state of affairs of concurrent development. You can do what's called fully synchronized objects. What that means is you synchronize all the methods on all of your classes. If you do that everywhere throughout every bit of code that you've got and don't use any classes from the platform which aren't fully synchronized, your code will be concurrent and type safe, and it will work.
Does anyone here work with JDBC or databases a lot? Yeah, so are you familiar with table locking versus row locking? Yeah, so doing this is like table locking for every single operation, including reads. Okay, so yeah, it's certainly safe.
How performant do people think the fully synchronized objects approach is? Hands up if you think you're going to get good performance doing that. Nobody. Right.
Okay, good.
Okay, good. The second approach is mutability. This basically says when you create an object, it has all of its fields must be final, and when you call the constructor, obviously that means you have to assign to every field in the object. After that, it may not be changed. So that means that if you need to modify anything on it, all you can do is make a new object with all of the values exactly the same and only the ones changed or altered. So that means that you are creating a lot of new objects. Every time you want to change an object, you have to create a new copy of it. And that's a lot of copy cost. And it also requires programmer discipline, because the platform, once again, is based on mutable state. It's not designed with the mutability in from the ground up. You have to add it in later.
So interestingly, we will make a little Java 8 point here that we're going to make in our talk. The new date and time APIs that are going to be coming out have been designed to be immutable. Okay, so every time you go to change a date or a date-like object in the new world of Java 8, you will actually be making a change on a copy. Okay, so it is inherently more thread safe than the existing date and calendar stuff. So yeah. There's a little tidbit for you from Java.
The existing date and time stuff is horrible. Java util needs to be taken out and shot.
Yeah.
So this leads us to the third alternative, which is really the only game in town. Be very, very careful. It sounds silly and flippant to say that, but actually that really is the state of the art in concurrent programming. Yeah. All you can do is to do the best you can, and that's why things like Java util concurrent are so important. Is because they provide you with a toolbox which has some additional safety built in.
Who here does some day-to-day Java util concurrent programming? Yeah, so quite a number of you. Keep your hand up if you're really confident in what you're doing.
Oh, good.
Nice. Few people who are very confident, that's good to see. So quite famously, when we asked this question at FOSDEM earlier this year, and we had people like Doug Lee in the room, Brian Gertz in the room, Mark Reinhold in the room, chief architect from Red Hat as well, I believe, nobody kept their hands up afterwards. This stuff is still really, really hard, so you're commendable for keeping your hands up.
Okay, let's talk about the JMM. This is the Java memory model, and this is a mathematical description of memory. And hands up if you've ever read any of the Java language spec. Okay, cool.
Seems to be the same people, doesn't it?
Yeah.
I think they're just like putting their hands up.
Yeah, and the JMM pretty much is the worst part of the spec in terms of impenetrability and lack of reading. Generics
gives it a run for its money, doesn't it?
Well, generics constraints are pretty bad, it's true to say. So in all seriousness, this stuff is actually pretty difficult to get an understanding of what it's really pinned upon. But one of the most important things to understand about it is that because Java was designed as a platform which was portable, the JMM actually represents a much weaker and more minimum set of guarantees than real hardware platforms. The JMM is not the same as the x86 memory model. The JMM it contains a great deal less in it and is a great deal less secure than x86.
Yeah. Which is actually a little bit scary, because there are other processor types out there, things like ARM, which is something that we'd all probably like to see Java get working on. And x86 kind of solves a lot of problems for us, and
it does.
It's quite scary stuff.
And there's actually an interesting Azul Systems, which Cliff Click and Jill Tanine and those guys They actually have quite an interesting product because they've got a JVM which is actually able to simulate hardware which has a much weaker model than x86. So they can take concurrent code, plonk it on their product, and then simulate it under conditions which are much weaker. And when you do that, loads of code which people think is concurrently safe turns out not to be. So in a sense, because most of us probably write code which sits on top of an x86 or possibly a Spark chip, we are in danger of being lulled into a bit of a false sense of security. Okay, so there are really four main concepts which make up the JMM, and they're synchronizes with, happens before, release before acquire, and as if serial. As if serial is pretty easy to understand. That means that the VM can play tricks and it can reorder instructions and it can do whatever it likes, provided that from the point of view of outside that thread, the order was unchanged. So that means that the semantics are unaffected by anybody that's outside the existing thread.
Almost a little bit like queuing in London, really, isn't it? You can arrange the internal order of the queue as long as the person who was at the front of the queue remains at the front of the queue at the end, then everybody's happy.
Yep. And release before acquire. This basically says if you want to do something atomic which involves two locks and a release and acquire operation, you do the release first and then the acquire. Happens before is kind of illustrated up here. This basically says that if two operations happen before each other, then X happens before Z. So that's sometimes called transitivity for those of us who have mathematical backgrounds. But the big one, the most important one, is synchronizes with. And here we have a few otters synchronizing with each other. This basically is the answer to the question, why synchronize as a keyword? The reason that synchronize is chose is because when you go into or exit a synchronized block, you must flush your view of memory back out to main memory into other threads. So that means that that's what's being synchronized. It's your view of memory. Okay, so should we do some Java util concurrent?
I think we should. Actually, just a quick housekeeping exercise. Does anyone here know what time this session is now supposed to finish since the keynote ran over? Nope? Okay, we'll just keep going until people kick us out. Or until they deliver beer.
Yeah, beer would be good.
All right.
Okay, so here we go. So here we have our dancing otter who's going to lead us through the API of Java util concurrent. And essentially these are building blocks for concurrent code. And this is almost like a basic vocabulary for building performant, safe concurrent applications. We're talking about locks and conditions and concurrency safe data structures and thread pools and things to actually execute our code. So let's start with some locks.
All right, so locks, I guess, can be seen as the basic way to replace the synchronized keyword. Now, that's actually a bit of a falsity, which Ben will explain further. But when you're trying to persuade people to stop using a synchronized keyword, generally speaking, a lock is one of the first things you want to introduce them to. So for those of you, I mean, most people here are Java util concurrent programmers, so this is all pretty familiar stuff. Basically, we want to go, there's a couple of threads who want to update some fields on one of our objects, okay? And in order to do this safely, we need to acquire a lock here, okay, which is a type of reentrant lock. Then we go and update some fields, we do some stuff, basically, nice and safely, because we've got a lock on it. And then finally, we unlock. Do not forget to do this.
Yep.
Okay, you have a distinctive problem. Now, an interesting thing about locks is that locks are actually objects, okay? So if you think about this, you can do things like pass them around. Okay? So there's a much greater level of flexibility there than with the synchronized keyword as well.
Yeah. So for example, one of my favorite examples of something you can do with a lock that you can't do with a synchronized keyword, it's called hand-over-hand locking. So suppose you want to update and mutate a large collection of objects. What you want to do is you only want to lock as minimally as you need to. So if you need to touch this object and the one behind it, what you do is you acquire the lock for the one behind it, and then acquire the one for the next lock, and then that one there, which means you can release this one. So that means that at any one time, only two objects are locked, rather than having to lock the entire collection. And that's not possible to do with synchronized because you don't have a way of expressing the lock as an object which can be handed around as a value. So that's quite a powerful technique. The reason it's called reentrant lock is because if you come up to the same lock again, if you're holding the token for it, you can go through. There are other locking implementations, such as p-threads, I think, which are not reentrant. If you come back to a lock, for example, in a recursive call, and even if you're holding the token to go through that lock, it won't let you. So that means that trying to write safe locking schemes is actually very difficult. My advice: there is actually a non-reentrant lock buried deep in Java util concurrent. Don't go anywhere near it. If you really think you have a use case for it, then come tell me about it over beer. But it's okay. So let's do some conditions.
All right.
And there's quite an interesting thing that needs to be brought out here.
Well, there's quite a lot of code in this one. So we've actually got two slides here to kind of show the two threads in action. So this slide is showing thread 1, which wants to basically put this object X into a nice array of objects. Right? Pretty simple stuff. And the other slide has got a thread which wants to take away from that array of objects. Yeah. So we'll go back to the first slide. Let's walk through some of this. So what we've got here is we've got the array of objects we've declared up here. Okay. And as I was talking about before with locks, we want to update an object or update an array safely with multiple threads. Therefore, we want to acquire a lock for it, which is exactly what we're doing here. However, we've got an interesting case here that if our array is already full, we can't put any more objects on it. Okay? So this is when we introduce something known as a condition, which we've declared up here, basically. And what the condition basically does is it says, okay, we can't actually progress any further, so what I'll do is I'll let go of that lock temporarily, and then I'll just with the while loop here, I'll just sit and spin and wait until someone tells me I'm allowed to go forward and actually put an item into this object array again. Okay? Yep. So basically what it's doing is it's waiting until there's a free space in that objects array.
So for people that are thinking in terms of how does this connect to classic concurrency, this is basically similar to wait and notify.
Yep.
One other interesting thing to point out is that the locks obviously are where you drive the conditions from. So in order to get a new condition, it's a condition on a particular lock. So that means that the instances of condition are tied to instances of lock.
Yep.
However, that doesn't mean that this is tied into an object itself in the same way that the synchronize keyword does. With synchronized, what you're actually doing is you're setting a lock which is attached to that particular object. Lock is just an ordinary object. So you are coordinating essentially a slightly different level, and it's not implicitly tied to these objects. When we create the lock object, we just create a lock object. We don't pass this as a parameter, so that it's not actually tied into the specific instance of lock.
Right. So for those of you wondering, how on earth does this condition get notified, get told that it's allowed to carry on, that it should reacquire the lock and actually put the item into the objects array? So if we go to what the other thread's been up to, okay, so imagine a second thread's coming along and it's taking objects from the objects array. So ignoring the case where it's empty, because it's just the reverse of the previous case I was explaining. Down here at the bottom you'll notice that the condition that we were talking about in the previous slide has now been signaled, okay? So back over here, we no longer have to wait. We can reacquire the lock behind the scenes and carry on through actually putting our object in. Okay?
Yeah. So if you imagine the case about one of the key questions you should always ask when designing a new bit of multi-threaded code is, what are my cases? How many readers are there? How many writers? And if you just pop back to the previous slide. Yeah. So imagine the case where we've got one reader and one writer. Okay? Fine. What happens to the size of the queue here? Well, basically, if both threads are running, let's suppose that we imagine there are two cores in the machine, one's putting, one's taking, the queue is probably not going to, if it's empty, it's going to stay empty. If it's full, it's going to stay full. If you imagine that for some reason another process interrupts on one of the threads, and that allows, interrupts the reading thread, and that allows the writer thread to get a whole bunch of objects on here. If these two threads are doing roughly the same amount of work, then it's going to be basically impossible for the reader thread to then acquire objects fast enough to empty the queue. So the queue state is probably not going to vary much. If there are objects on it, it's going to it's going to be fairly stable in terms of how many objects are on the queue at any one time. And thinking about those kind of implementation details
is very difficult,
pretty nasty.
Isn't it, Mike and Tricia? Yes. So if you want to hear about one particularly interesting way of getting around these sorts of problems, then there is a talk later on tonight, 5:20, is it? Yep. So come along for some more advanced stuff then.
Okay, right. Okay, so we've got some locks. So we've got the equivalent of synchronize, we've got the equivalent of wait and notify. You know, this is good. We've got some basic building blocks. Now let's talk about some data structures. So this one is the concurrent hash map. And basically, this is pretty much the main data structure that everybody starts with Java util concurrent. The reason being is it's pretty much a drop-in replacement for hash map, and everybody knows how to use a hash map. Because of the way that a hash function is structured, where you hash your key value and then do a lookup into a linked list, that means that there's an implicit parallelism there already, because all you have to do is lock one entry of the array. So you get parallelism pretty much for free just by the design of the hash map application. I mean, there is more to it than that, but if you're interested in the details, go read the concurrent hash map source. I wish you luck. But essentially, this means that there's a very nice way that this can just be slotted in to any code. I mean, you just use it essentially as a drop-in replacement for hash map. There are some interesting operations. There are atomic operations, so like put if absent, which basically is what you want to use if you're building up a large multi-threaded cache, because then that way you can just throw a whole bundle of threads at it. It doesn't matter if everybody's updating and people try to update the same values, because put if absent will protect you. Only the first thread will win. So that gives you a very, very simple and clean design for caches. Okay, so let's have a look at the corresponding list structure, which is copy and write array list.
This is the very, very safe way of dealing with array lists.
Yep. Yeah, we just tweak the slides slightly. So, okay, so in one thread we're adding some items, and in the second thread we're removing some items. Okay, all well and good. If we then take an iterator, after we've performed both of those operations, the iterator in the remove thread will see 2 fewer items. It won't see the one that it's taken out, but it also won't see the one that thread 1 added. And they will actually be dealing with iterators over what are essentially different copies of the list. So this means that your iterator is concurrent modification safe. And rather than throwing that, it just allows you to see different versions.
Who has seen the concurrent modification exception?
Yeah.
Yeah, we've all seen it, and you know, unfortunately, more often than not, it's been in my code previously until I started learning about some of the small modern concurrency stuff. So, yeah, thank goodness for this.
Okay. So, can anybody see a problem here? Yeah. Well, performance. If you're making a copy every time you modify, which is effectively meaning that your copy cost is going to go up.
Yeah.
So you should be careful about where you use this. Concurrent hash map basically is a drop-in replacement. This thing, you should only really use it if you know that your density of modification operations is low. If you're doing mostly reads, this is great because there's no modification, so there's no copy cost.
So if you're updating an entire massive array list for Twitter feeds coming in, don't use this. It's absolutely the wrong data structure to use. Yeah, so you have to think about which data structures you need to pick.
Okay, let's do the countdown latch. So this is one of a number, and there are some interesting new ones in Java 7 as well, of what I call group consensus constructs. What you want to do is you want to get to a point where everybody agrees that we're all at this point before the threads move forward again. And so we've got a whole bunch of otters lined up behind a fence here, waiting to be let out.
To the circus, for those who were at last night's session.
Yep. So basically, this is a very simple group consensus construct. You give it an integer when you spin it up, and then all you can ever do is count down. You can't ever increase that count after you've set it. You set it once at the start, and you count down each time one of the threads reaches the waypoint. And when everybody's at the waypoint, and that count reaches 0, everybody's released at once.
So the sort of use cases we're talking about here to try and put it in perspective is, are people here familiar with containers like the JBoss application server or WebSphere or whatever? So these sorts of strategies are used for basically notifying the app server when it's actually truly ready to go, right? So there's a thread spinning up, for example, the servlet container, one for the EJB container, one for the JCA container. we won't go into the debate whether this is actually a good design or not, but this is the sort of thing that you would use it for.
Okay, so quick example. So we've got some circus otters which are wanting to do something, and this is just a very simple thread. So these guys are set up. They're passing the countdown latch, and then basically when they come up, they wake up and then they count down. And this pattern of countdown and immediately followed by an await, it's very common. Because what that means is you've got a number of otherwise identical objects or threads which are doing slightly different versions of the same task, and you want to get them to all in the same place. The other place that I tend to use this a lot is in multi-threaded testing. Testing concurrent code can be really difficult, but you can actually, if you're smart, you can produce, I have to say, slightly verbose and long-winded unit tests, but you can actually produce genuine unit tests where you use a lot of latches to await some condition before sending in the next bit of data. So if you want to draw a sequence diagram where you actually have true independent processing, you can use the countdown latch in order to regulate those and to produce actual proper unit tests for them.
And for extra fun, I can recommend using a tool called JMeter to attach this style of testing to, and then you can really thrash your poor application to death, which is always fun.
Okay, the handoff queue. This basically is the standard way of passing messages or objects around between queues. And in fact, the general pattern here is thread pools connected by queues. That's pretty much how you design a large scalable multi-core application. There are some neat things here. You've got blocking operations. You've got back off and retry, and if you have a look in the Java doc, there's 3 or 4 different ways that you can actually interact with the queue. You can either throw an exception if something goes wrong, or you can return a special value, or you can you've got back off as well.
Yep.
There's a couple of others, and basically there are 2 main implementations of the blocking queue. There's the array list and the linked list backed versions. And they actually have very different performance characteristics. So if you're doing this in genuinely high-performance applications, you may want to watch which one you use. In particular, people tend to think, well, the array one will be faster because arrays are typically faster than just linked lists. But there's some odd things happen in the performance when you do that. If you're trying to use queues which are very fast, you may actually be better off using the linked list version. Obviously, with all performance-related things, what you should do is test it, write a proper plan, and conduct proper methodology. But I have seen some fairly odd behaviour on the array list version.
So for those of you who were at Dan Hardiker's earlier talk about the dark arts of performance tuning, where he hammers on about measure, that's what you need to do in this case as well.
Yep.
So measure before, try the different implementations, see what comes out afterwards.
Yep, and then we also have the shiny new transfer queue. Transfer queue is great. Basically what this says is, if you have 2 threads which are, one's sending, one's receiving, and they're going to go via a queue, basically check to see if you can do a direct transfer first, which is, it gives you a 15-20% more performance. It's quite a nice thing if you've got that use case. So this is just a bit of offering otters to make them go into the pipe here.
Yep. So if you find yourself, and I've seen a few people do this, when they start reaching for the JMS solution in order to do some asynchronous messaging, for some pretty small processes, then this is what you really want to be looking at instead. Okay?
Yeah.
So don't be afraid to do queuing work inside the JVM, inside memory itself. Okay? You don't always have to reach for the big heavyweight JMS toolbox. Okay,
executors. So if queues are how we link things together, executors are what happens. So what happens to actually execute our code. And there's quite an interesting thing here, because in terms of talking about what's coming in the future, currently we've got things which are essentially thread pools, and basically a callable and a future task. These are ways of modeling execution, but they're not the only ones that we have. So in a bit we're going to talk about fork and join, and that represents a slightly different style for how you actually execute.
Yeah,
and this is a trend that I think we're going to see more of. as we get more and more multi-core and more concurrent, we're going to start having the platform do more for us. So rather than actually having to write a lot of low-level concurrent code ourselves, we're going to have things like a managed thread pool, or a thread pool where we don't know how many threads are in it, or a fork and join pool, which potentially might break up the work and parallelize it in a different way to how we expect. That's a good thing, because one of the major advances that Java made was in memory management. When we first started using Java, we stopped managing our own memory, and we made that be something that the platform just took care of for us. And that's good, because our minds are not very good at handling a lot of boring, pedantic tasks. And memory management is a boring, pedantic task.
And so thread management, really, when it boils down to it.
Yep. So the concept that actually having a runtime managed concurrency is something that I think we're going to see more of, and in the trend through 8 and beyond, there's going to be more and more of this.
Now, I'll just point out one little thing. Most presenters will say that no animals were harmed in the making of this presentation. Unfortunately for this poor little guy here, he's a meal for an otter. So.
Okay, so let's just look at a bit of example code. I mean, this thing is, so this is a fairly standard bit of concurrent code you might write. I've got a queue of work items, which in this example I just take a string, and I've got a method to run a task that I'm handed. And all you do is you take in the task, you set the queue on it, and then you pop it into the thread pool, and the thread pool takes it away. So a queue reader task is probably something like a future task. It's certainly going to be something which is runnable. And then you return out a handle to the task so you can cancel it later. All well and good. Yeah, and that's our example task. And all that happens is you provide an implementation of do action, and when the loop is run, it just until it's shut down, it polls off the queue. So basically, this is effectively a queue draining task.
And look, an actual proper use of an exception. Woohoo.
Yep. And there should probably also be a shutdown method there. This pattern, by the way, of where you have a Boolean flag to control shutdown, and you don't actually, that's the mechanism by which you shut yourself down, is very common. The reason behind that is if you read in the very old Java doc for thread, you'll find things like stop and shut down. Yeah, don't ever call those methods. Have a read of the documentation and see why. But when you're dealing with multi-threaded code, you can't just stop and assume you're in a safe state. If you hand out the ability to uncontrollably stop another thread, you're almost certain to corrupt something. So that's why you have these patterns where you indicate that it's time to stop, you wait for it to finish what it's doing, and allow the piece of executing code to leave itself in a clean state.
It's sort of akin to trying to manually call the garbage collector in Java, right? It just doesn't do you any good. So,
well, I would say it can actually be harmful.
Yeah,
exactly. So essentially what you're doing is you're handing responsibility off to the task to say, you should shut yourself down now. You do that in whatever clean way is most appropriate for you, so to ensure that your state is clean when you shut down. Okay, let's...
Yes, and you are the second person to have pointed this out to us. Two presentations in a row.
It shouldn't
we
be.
still haven't fixed the slide.
Second thing, you cancel the after the exception. You should probably set back the after flag. This is also good practice.
Okay, yep. It's fair call.
Okay, let's do fork and join. Hands up if you've had to play with fork and join yet. Anybody? Oh, okay.
So this is a new Java 7 feature.
Yeah, so this is new with Java 7. Basically, what about MapReduce? Everybody know about MapReduce and large, huge distributed clusters of processing?
Things like Hadoop and stuff like that?
Yep.
Yeah, one or two people? Okay.
Yeah, that's cool. Okay, so basically, this is our first major example of a new way of handling concurrency, which is not really thread-like. So this thing, I mean, it is actually on top of thread pool, but the executions are in some sense smaller than threads. And it's very much hidden and behind the scenes. You can't really interact directly with the thread pool. You don't, under normal circumstances, even really know how many threads are in it. And you pass it objects which it's capable of breaking up. So the two that we have are fork join task and recursive action.
Yep.
Recursive action is normally the one that you want to use. The The idea for this, so just to describe the problem class in general, is imagine that you have a large array of things that you want to perform an action on. And the action of performing it on individual elements doesn't affect anybody else in the array. So that's an action which is obviously inherently parallelizable. And what you want to do is you want to do that efficiently across threads. So one of two things happens. Either you hand over just a few to one thread, and it just does all of those because the block is small enough that there's no benefit in splitting the block up, or you split the block up. And that essentially is at the heart of any fork join problem. It's that decision of, do I split this task up or do I handle it sequentially? So let's do...
so look at some actual code on this.
Yeah.
So what we've got here is a typical divide and conquer problem. If people remember quicksort from their computer science at university days, right? So this is kind of a rough parallelized version of quicksort. So let's say, for example, you're trying to sort a couple of 100,000 tweets from Twitter, right? So if your size is arbitrarily small enough, then you can just use the good old arrays sort method to do that for you. However, if the size of the array is deemed to be too large, you split the task in half. Okay? And then we use the magic invoke all method, and this is the fork join framework taking over for you. And what this basically does is it splits up the problem for you, makes the recursive call for you, but behind the scenes there's a thread pool, there's work scheduling going on, and it does clever things like work stealing.
So the idea is you've got a collection of queues where work that's going to be processed in a minute is waiting. And basically, if one thread, because the jobs on the queues are potentially of different sizes, some jobs will be small jobs which are ready to actually be run serially. Others will be jobs which need to be split up again. So the amount of time that each individual thread is spending processing tasks can vary in a non-deterministic way depending on what size of jobs it had. So let's suppose that a serial running job was twice as quick as a split job. Then what that would mean is that some threads are basically going to become idle before others, because what happens to be on their queue is just mostly small jobs. Yeah. And then when the queue's empty, that thread under normal circumstances will be idle. But the algorithm which is used for this actually enables threads to steal work off the back of somebody else's queue.
And you can imagine trying to write that yourself. That's pretty darn difficult.
Yeah.
Of course, at the end, you would have to provide your own merge algorithm to put that all back together again.
Everybody's seen a merge sort algorithm. We're not going to show people merge sort.
So we'll go through. So.
Okay. Basically, this is sort of a kind of a roadmap for where we are. Mutable state is protected by locks. You have concurrent data structures, and you have to be very careful with performance for, especially with the copy and write array list. You have synchronous multi-threading, and you have asynchronous via queues. You have executor-based thread pools. And concurrency is key to the future of performant code, and mutable state is very, very hard. But the JMM is a good, low-level, flexible model. Okay, so we've only got a couple more secs, so let's come on to these last two slides. The runtime, imagine if the runtime was able to help you out more. Imagine we were able to reach true runtime managed concurrency, and the collections were thread safe by default. And what if thread wasn't the default choice for a unit of concurrent execution? If you think about it, thread is not a great choice of a high-level primitive. It's a very low-level primitive. In some senses, it's like the assembly language of concurrent programming. And there are other models which could be used, but there's probably, unfortunately, not much we can do with Java. We're stuck with a lot of heritage. The JVM and the JMM are very sound. And these frameworks where more is done behind the scenes and you don't have to care as much are probably the best that we can do, because all of this will still have to coexist with code, which unfortunately is stuck in classic world. But if you wanted to dream of a new language, it should be on the JVM, and it should build on what we've learned in 15 years of trying to develop applications with Java.
I wonder if we have any of those languages around.
Yeah. Okay.
So we've got Scala. Who here's doing some Scala work? Yeah. Anyone a Lisp fiend doing some closure work?
Yeah.
Yeah. And we know there's a GParse fan sitting down in the front there. Yay! Yep. So there are lots and lots of really, really good options on the JVM.
And this is where the work of the future that we'll eventually see in Java is going to start from.
Yeah.
These languages are more frontier and more experimental. Java is by its nature very conservative. But if you are interested in large scale application, concurrent application development, have a look at one of these. Okay.
Cool.
I think we're out of time.
Thanks for listening, and sorry for the change in schedule.